Thanks organizers for possibility to give a talk. Let NR be the set. My screen is visible.
Yes.
Yes.
Yes. Yes.
Let NR be the sets of natural and real numbers, respectively. C be the complex plane, C bar be its one-point compactification, U be the open unit disk, and R plus from 0 to infinity. Let function f of z meromorphic in unit disk maps univalently disk onto the domain B such that f of 0 equals a, f prime of a from R plus, where a from B. Then the value R big of BA is module f prime of 0 is called conformal radius of the simply connected domain B with respect to a point A from B. Conformal radius of the domain B with respect to an infinitely distant point is R big of B infinity equals R of phi of B 0, where phi of Z equals 1 over Z. In 1934, Lavrentiev proved the following theorem. Theorem 1, let A1 and A2 be some fixed points of the complex plane, and BK, AK from BK, be any non-overlapping simply connected domains in C, then the following inequality holds. R of B1 A1 times R of B2 A2 is less than or equals module A1 minus A2 squared. Equality in this inequality occurs only in the case when the domains B1 and B2 are two half planes and the imaginary axis is their common boundary, and points A1 and A2 are symmetrical about their common boundary. Many authors investigated this result in different directions. For example, in the monograph by Schiffer and Spencer, a whole chapter is devoted to the study of Lavrentiev's theorem. From the proof of this theorem as a corollary follows the well-known statement of Koebe-Bieberbach in the theory of univalent functions. Later, for example, in monograph Schiffer and Spencer, Lavrentiev result was generalized to the case of meromorphic functions. Lavrentiev considered regular functions. If we have meromorphic functions, then for domains B1 and B2, the inequality 1 is valid, and equality in 1 is attended if B1 and B2 have the following form 2. An example of such configuration of the domains is the case when one domain is bounded by some circle, and other is a complement to the first domain. It should be noted that for the case of meromorphic functions, there is no unity of extremals. We have a whole continuum of extremals. Consider definition of a quadratic differential. Let G be a domain in complex plane. By a quadratic differential in G, we mean the expression Q of Z dz squared, where Q of Z is a meromorphic function in G. A circular domain for quadratic differential is called a simply connected domain G, containing a unique double pole of a quadratic differential in a point A, such that at univalent conformal mapping, the domain G onto the unit disk, the identity holds Q of Z dz square equivalent minus cut d omega squared over omega squared, k from R plus. Then in 1952, Kolbina summarized Laurentiev results by taking functions in fixed positive degrees. Then for any finite different point A1 and A2, maximum of the value 4 is attained for functions mapping unit disk onto the domains that are circular domains of the quadratic differential 5. And Kolbina proved inequality 6. When we have sign equal, XML configuration is shown on the picture E and F when alpha is less than beta and alpha is greater than beta. Consider generalization of conformal radius for multiply connected domains. A function g of b of z a, which is continuous in extended complex plane, harmonic in b without a apart from that, vanishes outside b, and in the neighborhood of a has the symptotic expression g sub b of z a equals minus logarithm module z minus a plus delta plus infinitesimal value when z tends to a. Is called the classical green function of a domain B with pole at a from B. The inner radius r small of BA of the domain B with respect to a point A is the quantity e to the delta. Since the green functions is conformal invariant, if the function f maps the domain B conformally and univalently onto a domain f of B, then R of BA modulus f prime of A is R of f of B f of A for each A from B. The inner radius increases monotonically with the growth of the domain. And it is known that the following inequality holds. Modulus f prime of 0 is less than or equals R of BA. In previous works, we were considering systems of points of the unit circle or circle of the radius R. And radial systems of points when we have n rays and each ray has 1 point, and m radial systems of points when we have n rays and each ray has m points. In this work, we consider any fixed system of points of the complex plane. For example, it is p rays on each ray, and each ray has a different number of points. And sum of these points equals n. This presentation is devoted to obtaining evolutionary inequalities for the functional In of gamma, Hn of gamma, and Jn of gamma for all values of the parameter gamma from interval 0 n, where n natural number, an be an arbitrary fixed system of points of the complex plane, and the domains is the arbitrary system of mutually non-overlapping domains. These functionals have been studied in many works under different conditions, but currently there are no methods for obtaining the maximum for gamma from R+. Consider the functional In of gamma equals R of B00 to the gamma product RBK AK, where n natural number n is more than or equals to gamma from interval 0 n, A0 equals 0, an be any fixed system of points on the complex plane. Bk be any collection of mutually non-overlapping domains such that ak from bk k from 0 to n. Then we use a mapping 1 over z to this system of points and domains. Let D of E be the transfinite diameter of a compact set E. It is known that the logarithmic capacity coincides with the transfinite diameter of the set E. And for compact E, its logarithmic capacity is determined by the following equalities. Capacity E equals 1 divided by R of C bar minus E infinity. If the value R of C bar minus E infinity is finite, and capacity E equals 0 otherwise. Then R of B00 equals R of B0 plus infinity equals 1 divided by D of C bar minus B0 plus, where domain B plus is the domain of the mapping 1 over that. Then by virtue of the well-known polar theorem, mu of E is less than or equals P d of E squared, where mu of E denotes the Begue measure of the compact set E. This yields inequality 9, and thus we obtain that 1 divided by D of C bar minus B0 plus is less than or equals 1 divided by square root 1 over P mu of C bar minus B0 plus. Then using monotony and additivity of the Lebesgue measure, from previous inequality, we have that R of B00 is less than or equals 1 over P sum of mu B bar K plus to the minus a half after mapping 1 over Z. By the theorem on minimization of the area, mu of B is more than or equals PR of BA squared. Then we have inequality 11, but in this inequality we don't know how change in the radii after the mapping. And taking into account an invariance of green function in conformal and univalent mapping, we get equality 12. Then by substituting 1 over that and calculations, G green functions, G B K plus of omega plus AK plus is logarithm 1 over module Z minus AK plus logarithm module AK squared R of BK plus AK plus plus infinitesimal value. And we obtain that after mapping 1 over that in a radius R of BK plus AK plus is R of BK AK divided by module AK squared. And we arrive at the inequality 13. Then for denominator in this inequality, we use Cauchy inequality of arithmetic and geometric means. And 1 over n sum of R of BK AK squared divided by module AK to the 4 is greater than or equals product R BK AK squared divided by module AK to the 4 to the 1 over n. And we obtain that our product In of gamma is less than or equals n to the minus gamma over 2 product RBK AK to the 1 minus gamma over n, and product module AK to the 2 gamma over n. And finally, we the dynamic inequality 15 holds. Then the following theorem is valid. We obtain the following theorem too, where functional In of gamma is determined by initial value of the functional In of 0. Let n natural number gamma from interval 0 n. Then for any fixed system of different points AK, and any collection of mutually non-overlapping domains BK, AK from BK, K equals from 0 to n, A0 equals 1, the inequality holds. An of gamma is less than or equals n to the minus gamma over 2, In of 0 to the 1 minus gamma over n product module AK to the to gamma over n. The inequality 16 holds also for gamma from R plus, only for fixed points and fixed domains, or fixed in a radii of the domains with respect to a point A. Note that in the paper of Bakhtin Zabolotny in Ukrainian Mathematical Journal 2021, for functional In of 0 and A is more than 2, the estimate 17 was proved. And combining inequality 16 and 17, we obtain corollary 1 and inequality 18. From theorem 2, for gamma equals n, next result is true. Let n from n, then for any fixed system of different points AK, and any collection of mutually non-overlapping domains BK, AK from BK, the inequality holds. R of B0, 0 to the n product K from 1 to n, RBK AK is less than or equals n to the minus n over 2 product module AK to the square. Inequality 19 will be referred to as the generalized Lagrangian inequality, because for n equals 1, the corollary 2, we have a Lagrangian result. Let module AK is less than or equals rho from R plus, and in a radii are equals. Then under all conditions of corollary 2, we obtain inequality R of B0, 0, R of BK AK is less than or equals 1 over square root n times rho squared for every k from 1 to n. And remark 2, in corollary 3, by Lagrangian theorem, we have R of B0, 0, R BK RK is less than or equals rho squared, k for every k from 1 to n. And we move to evolutionary type inequalities. From theorem 2, for functional In of gamma, inequality 20 holds. It is clear that R of gamma, R of B0, 0 to the gamma, product RBK AK is R B0, 0 to the tau, R of B0, 0 to the gamma minus tau, product RBK AK. Then to the value in parentheses, we use inequality 20, and after calculations, we obtain inequality 21. Hence, the next result follows. Theorem 3. Let n natural number n is more than or equals to gamma from interval 0 n and tau from interval 0 gamma. Then for any fixed system of different points of the complex plane and any mutually non-overlapping domains bk, points ak from domains bk, k from 0 to n, and a0 equals 0, the inequality in of gamma is less than or equals n to the minus gamma minus tau over 2 times in of tau times in of 0 to the minus gamma minus tau over n times product module points ak to the 2 times gamma minus tau over n. In this case, functional in of gamma is determined by initial value of the functional in of gamma and intermediate value of the functional in of tau. Using similarly to the proof of the theorem 2, the following results is true for functional Hn of gamma. Let theorem 4. Let n natural number, n is more than 2, gamma from interval 0 n and tau from interval 0 gamma. Then for any fixed system of different points ak, and for any collection of mutually non-overlapping domains b infinity, bk, infinity from b infinity, ak from bk, and k is from 1 to n. The inequality holds Hn of gamma is less than or equals n to the minus gamma minus tau over 2 times Hn of tau times Hn of 0 to the minus gamma minus tau over n. And as consequences of theorem 3 and theorem 4, we obtain the following result for functional Jn of gamma. Theorem 5. Let n natural number, n is greater than or equals to gamma from interval 0 n and tau from interval 0 gamma. Then for any fixed system of domain of different points ak of the complex plane, and for any collection of mutually non-overlapping domains b0, b infinity, bk, a0 equals 0 from b0, infinity from b infinity, and ak from bk, ak from 1 to n. The inequality holds. Jn of gamma is less than or equals n plus 1 to the minus gamma minus tau times n plus 1 divided by n plus 2 times Jn of tau times Jn of 0 to the minus 2 times gamma minus tau over n plus 2, and times product modulo of points ak to the power 2 times gamma minus tau over n plus 2. In this inequality also, functional Jn of gamma is determined by initial value of the functional Jn of 0 and intermediate value of the functional Jn of tau. Thank you for hearing me.
Thank you very much, Iryna, for beautiful talk.